Alrighty, y'all. Today we're taking a look at the recitation for March 23rd. And for this one, we're going to be looking at the work energy theorem and applying it to some different situations. Okay? And I know it says April 16th, but it's March 23rd. So if we're going to be applying it to some situations, we're going to have to start thinking about how work, like, is it positive or negative in certain situations. So remember, our equation for work is our force vector dotted with our delta x, or dotted with just our displacement, right? However we're writing it, but it's a force vector that's a dot product with our displacement vector, however we choose to write that displacement vector, right? And if they're going in the same direction, that's when we have positive work, right? And if they're going in opposite directions, that's when it's negative, right? Because if they're going in the same direction, it doesn't matter how we define our coordinate system. If I say up is positive, down is negative, right? They're both going in the same direction, they're both gonna be positive, so when I multiply them together, a positive times a positive gives a positive. But if I flip it, and I say this is positive, and this is negative, right? Now we have a negative vector times another negative vector. A negative times a negative still makes a positive. But then if I flip them, right, they're going in opposite directions. It doesn't matter which way I set as my coordinate system. I'm always going to have one positive, one negative. A negative times a positive equals negative. Right? So that's what we're thinking about going into figuring out some of these situations. Right? We're thinking about how do we make it so the force is going the direction that we want relative to our displacement. So the first thing we're going to talk about, we have our kinetic friction doing positive work. And remember, positive, we said they're going in the same direction, right? So kinetic friction doing positive work sounds a little tricky at first because, well, we know kinetic friction is supposed to oppose the direction of the motion. That's what friction does. But it's only opposing the direction of motion relative to the thing that is putting friction on it, right? So if I have a bunch of dishes on a tablecloth, right? So here's my tablecloth, here's a spoon, that's quite the spoon, but if I have the tablecloth and I pull the tablecloth out from under the dishes, the kinetic friction of the tablecloth acting on these dishes is going to want to pull that way. So this is our direction of our force, is to the right? Because I'm pulling the tablecloth this way. So our direction of friction, kinetic friction, as the tablecloth slides out from under these dishes, is going to the right. But I'm not super good at pulling the tablecloth out from under the dishes, so they don't stay perfectly still. They move a little bit and go this way. Right? So they move a little bit with the tablecloth, but they don't go flying off the table. So now here's our displacement, here's our force, and they're going in the same direction. That's our kinetic friction doing positive work. Now we think about static friction doing positive work. And again, static is when something's not moving. And if something's not moving, it means our displacement is zero, which means our work should be zero. But again, this is only static relative to the thing applying the motion to it. So if I'm like just standing on a boat in the middle of an ocean, here's my boat, and I'm standing on it, there I am, in the water, right? The boat's going to be moving this way. I'm going to be moving with the boat. And, I mean, the boat has some, like, motor that's giving it the thrust. That's putting a force on the boat, but then the boat is putting the force on me so that I move with them. So that's the friction force that's pulling me along with the boat. Again, we have our force from our static friction and our displacement going in the same direction gives us positive work. And air resistance. Again, this is kind of a tricky one because we think of air resistance as always slowing something down as it flies through the air. But really, we're just using this as like a common term for air acting on something. So, I mean, if we wanted air resistance to have negative work, if I just had anything, just like, say, a building, right? There's our building. And we have just wind blowing on it, right? There's a force from air resistance, because that's air pushing on the building. But the displacement, the building's not moving, so our displacement is zero, which means our work is zero. But that's not what we're looking at right now. Instead, I'm going to go back to our boat example, and now we have a sailboat, right? The wind catches in the sail, and it causes the boat to go this way. So we have our air resistance force from air resistance pushing on the sail, which causes the boat to be displaced in this direction, both going in the same direction, positive work. Now let's look at a normal force doing negative work. Right, so we have a normal force. So here's just the floor. We have the normal force pushing up this way. Well, we want it to be negative work. So if we're standing on the floor and the floor is pushing up on us, we want it to be negative work. We know we need to be going that way. So in what situation do we go this way, but we're still touching the floor? I'm going to say we're in an elevator, right? I'm standing in the elevator, and the elevator's going down. I'm going down with the elevator, but I'm not in free fall. The elevator's still holding my feet on the ground. So we still have a force, normal force, pushing up, but our displacement is down. Therefore, we have negative work. Now, exact opposite. We want a normal force with positive work. We want a normal force going in the same direction as our displacement. So the same exact kind of idea, we can just be in an elevator, but this time instead of going down, we're going up, right? Because our normal force is still pushing up on our feet, but now we're going up as well, meaning our force and our displacement are in the same direction, gives us our positive work. Now tension doing positive work, right? This is like if I have anything attached to a rope. Let's put a bucket on a rope. Here's our rope. So our tension force, but in this case, here's our bucket, and the tension force is pulling up on the bucket. I'm talking too much about boats. Tension force is pulling up on the bucket, and we want it to do positive work. So we want our displacement to be the same direction as our force. So what we can say is it's just a bucket moving upwards. If we're using this rope and pulling the bucket up, displacement and force in the same direction gives us our positive work. Tension doing negative work, again, it's the exact same but opposite. Right, we have our bucket on a rope. Our tension is still pulling the bucket up, but if we're lowering it down, say from a treehouse or something, here's our force from tension, and here's our displacement over here. Right? Force is going one direction, displacement's going the other, opposite directions, gives us a negative work. Tension doing zero work. So now we think about what can make our work be zero. So we have our equation down here with this dot product. A thing to remember about our dot product, right? We're not just multiplying the magnitudes, because these two things are both vectors. When we do a dot product, really what we're saying is we're doing magnitude times the magnitude times the cosine of the angle between them. And this theta, it's very important. Here's our force, here's our displacement. That's this theta. It doesn't matter if I'm on a hill and we already have a theta here. It doesn't matter anything about this problem. It's always just the difference between the angle between the two vectors. That's what we're thinking about when we say theta, right? So this is really our equation that we're thinking about making go to zero right now. So we know there's tension. We know there has to be tension, otherwise the tension is not doing the zero work. So tension cannot be zero. So we have to think about either a situation where our displacement in the direction, our displacement is zero, or cosine is zero. Cosine of theta is zero. Well, cosine of theta is zero when theta equals 90 degrees, or pi over 2 radians, right? So either our force has to be perpendicular to our displacement, or there's just no displacement, right? So if there's no displacement, this could be anything of just, I was saying I was holding a bucket before and pulling it up a tree and all this stuff, but if the tension's pulling up on it, but the bucket's just not moving, our displacement is zero, so our work is zero. But also, if I'm swinging something around in a bucket, like on a rope, like when we had the frog in the bucket, if I'm swinging this around in a circle, the bucket, I drew the circle really poorly, but this bucket's not going in the direction of the tension. It's not displacing towards the center of the circle. It's just going around. And like when we said, our velocity is going to be perpendicular to this acceleration towards the center. That's what we were saying. We can say that this work done is zero because our displacement is generally in this direction. It's always going to hold perpendicular no matter where we are. there's our perpendicular to this force. So this is another situation where our work done by tension would be 0. Now traction doing 0 work. This is again like something like static friction doing 0 work, meaning either our displacement has to be 0 or our angle between them has to be 0. So the way I thought about this was I just said if there's a person and they're kind of like leaning on a wall, right? They're pushing on the wall's pushing back on them, right? But they're not moving, they're just leaning on the wall. So some other force, so we have some of our forces on this person. Here's my force diagram for the person. We have the wall pushing on their hands. We have the floor pushing up on them. We have gravity pulling them down. But we're not moving, so we know something has to balance this. That's going to be our friction. So, gravity, normal force from the floor, and this is the normal force from the wall, right? Force from friction. That's our static friction. That's pretty much what traction is. So that's what I said when it's doing 0 work, because we're not moving, we're just leaning against the wall, but we're doing 0 work because our displacement is 0. And this is an example, this was on your packet, it's not on mine, but gravity doing negative work. Right, gravity would be doing negative work. Gravity is going to be pulling us down, so it's whenever something's going up. So we throw something up in the air, like we throw a ball, and it goes up. But it's only going to be negative work while the ball is going up. Once it starts coming down again, then we get positive work because our displacement is in the same direction as gravity. All right. We got through all of our examples. Now it's time to actually start thinking about the work energy theorem and how we're going to be using it. Right? And again, when it says our cosine theta, it's very important. That's the angle between the two vectors, not just whatever angle we happen to find. So we have a penny and we're dropping it off the Empire State Building. The urban legend that if it falls, it could kill someone is actually false. And we'll actually kind of find out why, because, well, it's because of air resistance. Right? The penny has some terminal velocity, but that's really why. So 2.5 grams sets off a bit of a red flag, right? Because we don't want our mass in grams, we want it in kilograms. So it's going to be 2.5 times 10 to the negative 3 kilograms, right? Which is 0.0025 kilograms. So now we're in good units. Now we can start thinking about what the question's asking, right? With what velocity would it have struck the ground if there was no air resistance? So this is real life. We're given a situation in real life. So there is, and it says there is air resistance. So we're thinking of a magical hypothetical situation where there's no air resistance. So in this perfect world, right, let's set up our work energy theorem. We start with our initial kinetic energy, 1/2 m v initial, I'm going to use naught actually, v naught squared, plus all of our work done, I'm just going to use a big W to remind me that I haven't figured that out yet, equals our 1/2 mv final squared. Right? Our initial energy plus whatever change is happening to our system has to be our final energy. Well, the work is caused by forces acting on the penny. While it's falling, we already said we're neglecting air resistance, so the only force acting on our penny is gravity. So the only thing we have to worry about is our work from gravity. Right? And we said our work is going to be force times distance. Our force due to gravity is mg, and our distance is whatever distance we travel in that direction. We drop it off the Empire State Building, it hits the ground 380 meters later, right? So that's our force times our distance. Now I just plugged these numbers in, but now I'm going to actually think real quick about whether this is a positive or negative work. Right? So we know our force from gravity is pulling the penny down, right? And the penny's also falling down, right? So we have our two vectors going in the same direction, which means this is a positive work. Now let's think about what else we know in our big equation. So we're solving for this final velocity because it's asking with what velocity does it strike the ground. So this is what we're solving for, so we're not supposed to know that. So we need to figure out our v naught. Since we're dropping a penny, it's just going to start from rest, meaning our V naught is 0, and this whole term is just going to go away for us. So now I'm going to write out our new equation with everything that we just figured out. So we said that initial energy is 0, so it's going to be plus our mg times 380, and that equals our final kinetic energy, which is our 1/2 mv final squared. And lo and behold, we have a mass on both sides, so we can just divide that on out. Now we don't even have to worry about the fact that it's in the wrong units. So I can just ignore it and plug in. So now I'm going to solve this thing for this V final. So I'm going to get 380 times 2, 760 times g, and we take the square root. That's our V final. And if I punch this into my calculator, right, it's going to give me 86.34581634 roughly meters per second. And we kept everything in base units, so it all works out in the end. Wonderful, wonderful. Now we have to figure out the work done by the drag force. This one's a little bit trickier, so let's just set up our work energy theorem the same way, and then we'll break it down again. So we have our initial kinetic energy, 1/2 mv naught squared, plus, again, our big work, because we don't know what's being done just yet, but we're just saying there is work being done, equals our final kinetic energy, right? So now let's break down this work. Now that we're not neglecting our drag force, we have two forces acting on the penny as it falls. We have our gravity, still the same as before, mg. I'm just going to use h to represent this height. It's the height of the building. We still have that gravity, still positive work because we're still falling, but then we have some work from our drag force. Okay? This is going to be a negative value, but I'm not going to worry about that right now. I'm just going to say work from drag and solve it out and see what happens. Okay? And again, we're starting from rest, so that'll go away. So now I'm going to plug in everything we have, right? So we have our mgh plus our work from the drag force equals 1/2 m. Oh no, we don't have the V final. Well, we solved for one before, but there we were neglecting air resistance, so it doesn't make sense to try to use it in here when we have air resistance. But we were given, it was our given that our air resistance, with air resistance, we ended up with 50 meters per second. So this is going to be our V final when there is air resistance. I'm just going to call that V2 for right now. So I know this, I know the mass, I know my G, I know my H, and I'm solving, sorry, that's a subscript, not a second letter. Now, and I'm just solving for this. So it's one equation, one unknown. But there's another way to look at this, and I'm going to just bring that up real quick, right? Remember, there's multiple ways to solve systems of equations in algebra. If I'm looking at this, I'm going to pull my equation from before. Right? If I say from before, if I have no air resistance, I'm going to say mgh, right? Again, I'm just using h for that, equals 1/2 m, and I'm going to call this v1 squared. Now, if I pull this down here, what I can do, same way I would in algebra, make this negative, and I'm going to multiply this in on both sides and see what happens. Okay, so I'm doing mgh minus mgh, that's going to disappear. And then on this side, I'm just going to be left with our work from the drag equals 1/2 m v2 squared minus 1/2 m v1 squared. And essentially what this is saying, what this is telling us is these two situations, the difference between the situations is this drag force, which is true. The first time we had no air resistance, the second time we did have air resistance. And this is our different end states of each. So this is causing the two differences between them. But we can just finish solving this out with our work energy theorem up here as well. That's another thing to point out, just to keep an eye on. Okay. So if I plug in, if I solve this for, I don't know why I keep writing that like a letter. Then we have 1/2 m v2 squared minus mgh. All I have to do, I have to plug all of this in. And if I do that, right? That's going to give me negative 6.1945 joules, which makes sense. I said it at the beginning. Our drag force is going to be up, but our displacement is still down. They're going in opposite directions. It should be negative. We should spit out a negative number. I just like to always keep all of my work positive until I solve it out, because then if it gives me a negative number, I know it's negative work. But if I think it's negative at the beginning, but I was wrong, and it gives me a negative number, that kind of gets confusing, and I always mix up my signs. It doesn't matter what you choose to do, just keep it consistent and remember what you're doing, and it'll be fine. But that's just the reason I kept it positive at the beginning. It gave me a negative value because it's going to be negative work from the drag. Now, the penny hits the sidewalk and digs into the surface 2 centimeters deep. What is the upward force exerted on the penny by the pavement? Again, I'm just going to real quick while I'm thinking about it. This is 2 times 10 to the negative 2 meters, right? Because we want to keep everything in base units. So now let's think about what's going on. So right before it hits the ground, the penny's going some speed, and now it digs into the pavement, and something happens. There's work done on it. There's forces acting on it, and then we have some final state. So let's think about our initial state. Is going to be our kinetic energy of 1/2 m. And it's going to be our V2 squared, because this is real life. We said it hits with 50 meters per second. So that's why I specified that V2 is at the 50. Right? So right before it hits the sidewalk, that's how fast it's going. And then while it's in the sidewalk, we have some kind of work going on. That's going to give us our 1/2 m V final squared. Right? And since it's just getting stuck in the sidewalk, our final velocity is going to be 0. So that term's just going to go away. Now let's think about what work is being done on it. So it's still on Earth, so we're still going to have some work from gravity. And we're still going down during this time that we're going into the pavement, and gravity's still pulling down on us. So it's still going to be a positive mgh. I'm going to call this mgx for this one, right? Because we used h for the height of the building. I don't want to get that confused, because this is now our 2 centimeters. But we also have another thing doing work on our system. We have the work from the pavement, because that's what we're looking for. We're looking for the force exerted on the penny by the pavement. So let's think about what work the pavement does. The pavement's going to be pushing up on the penny, but while it's falling into the pavement, it's still going to be going down. So while it's slowing down, it might be slowing down, but it's still moving downwards. So while it's in the pavement's going to have a negative work on the penny. And what's our equation for work? It's going to be our force times, when I said it was x. So whatever force from the pavement times x, this displacement, that's the magnitude of our work, and I just said it was a negative. Okay. And this one I am going to say is negative to start off with. I know I didn't before, because this one I'm taking another expression and plugging it in for the work. This variable I'm going to keep positive, but when I plug in for it, I'm going to think about positive or negative. You don't have to, this is just how I choose to do it. So now I'm going to plug all this into our equation, right? And we get 1/2 m v2 squared. Remember, we know our v2 because it's given in the problem. That's our 50 meters per second, plus our mgx, and our x is this 2 centimeters. And that equals, that minus our fpx, and that equals, we said our final kinetic energy is 0. So now we solve this whole equation for this force, because that's what the question's asking for, right? The force exerted on the penny by the pavement. So all I do now is I solve this. It's one equation, one unknown. I solve for that force, and if I plug everything in, I get my force from the pavement is 156.274525 newtons. Right? And we want to keep our units, right? Energy is in joules, force is in newtons, velocity is in meters per second. Now, let's take a look at that next question. We have an object at rest being pushed up a incline. The thing is that's a little tricky about the wording of this. We're not pushing it all the way up the incline. We're only pushing it enough to give it some initial velocity, and then we're looking at it, the time that we're looking at is when it's just moving up and down the ramp without us pushing on it. So I'm gonna start, here's our object. Really exciting, I know. It has some initial velocity going that way, and then that's our state 1, I'm gonna call it. Then at the top, this is what I'm gonna say is state 2, and that's gonna be, I guess, V2, because I said that. But that's when our velocity equals 0. When it's at the very, very top, right before it turns back and falls down, our velocity is gonna be 0, and that's the time, that's the instant we're looking at. And we're saying there's no friction to start off with, so we want it to travel a distance d up the incline. All right, so here's our distance, and also the incline was at some angle theta. I think it said, yeah, we're using this theta. So we have a whole lot of information. Let's think about what forces are acting on the thing while it's going, right? Because that's what's going to give us, when we set up our 1/2 m v naught, actually I'm going to call this v1, right, because I said this was state 1 over here. So v1 squared plus, again, all of our work equals 1/2 m v2 squared. You know our mv2 squared is 0, so we can just do that. So let's think about what forces are acting on this thing while it's going up. We can draw our force diagram. We have gravity and then our normal force, right? And force normal. So we have to think about the work done by each of them. So we have work from gravity and work from our normal force. Work from gravity is fairly easy, right? We want to take a look at how we're displacing in the this way direction. Right? We're saying gravity is going along this y-axis. I'm not tilting the axes just yet. Right? Gravity is going along this y-axis. Let's figure out what our displacement is on that axis, right? So gravity is going down, but we're going up the incline, so we know that in some sense it's going to be negative. But if I take this and just bump it on over here real quick, if I'm looking at my starting position here, my ending position here, I kind of just draw a dotted line there. This is our change. This is our y displacement. This is how far we're displacing in the direction that gravity is acting, right? So I'm going to call that h. I mean, we can do some trig to get that because we have a hypotenuse and we have an angle. We'll do that in just a second. I'm going to start just by thinking about this. All right, we said gravity was negative work. And again, our force from gravity, mg, and our force and our displacement in that direction is h. And we're going to get values in terms of things that we know in just a second. But first, we're going to think about our other force. Let's think about what work that this normal force does. Now I am going to think about tilting my axes, so I'm going to start looking at things this way and this way. Okay? The same way I said gravity is acting like this, and I found the displacement in that direction. Now, normal force is acting on this line, so we have to find our displacement in that direction. But the way we're displacing, right, we're going straight up the hill. So if this is our angle between our displacement and our normal force, our displacement and our force vectors, our force and our displacement vectors, that's our angle between them. It's going to be perpendicular. That's 90 degrees. That's our cosine of 90. We're not displacing in the normal direction because there's 90 degrees between them. Cosine of 90 is 0. Our work done is going to be 0 because we're not jumping up off the ramp, moving in this normal direction. So we get to say that is 0. So now it's asking what velocity we had to slide it with in order to get at this distance. So we're solving for the initial velocity. So I'm going to solve this equation, plug in, solve this equation here. I'm just going to, this is a negative on this side, I'm going to add it to both sides, so I can say that it's 1/2 mv1 squared equals mgh. I can divide the mass out on both sides, again, because we're not given the mass, so we should probably not have it in terms of mass if we don't know what it is. And now let's think about what this h is as well, because that's not in terms of our givens. So if I'm setting up my triangle, I have h, my hypotenuse, and some theta. Sine of this theta is opposite over hypotenuse, meaning that sine theta equals h over d, which means h equals d sine theta. Right? So we have, I'm going to multiply both sides, v1 squared equals 2g d sine theta, and just to isolate our initial, I'm going to take the square root of both sides, and this is our answer for this one. Okay. Now, when it reaches the base of the incline again, how will the velocity compare to the initial velocity? Well, without doing any math, we say that as it goes up, gravity does some negative work on it and slows it down. But as it goes down, it's traveling the same h. So gravity is doing the same work that it just did, but in the opposite direction, so it's going to speed it up the same amount that it's slowing it down. So when it hits the ground again, or when it comes back down to the level, it's going to have the same velocity. Oop, I did not mean to undo that. It's going to have the same velocity. So now we have friction. So in this case, we're going to start thinking about, we can have the same exact picture. I'm going to pull all of this in the same way. Same exact picture, but a different force diagram this time. Because now instead of just our gravity and our normal force, we're also going to have, right, we're going between 0.1 and 0.2 for right now. We need to, here's our force from friction, here's our normal force, and here's our gravity. So now if we're doing 1/2 mv1 squared, plus our work, we're having work from gravity, our work from our normal force, and our work from our friction force. And that's going to give us our final energy, 1/2 mv2 squared. And again, it comes to rest at the top, so our final velocity is 0. Same thing, we're not jumping up off the ramp, so our normal force, our normal work is also 0. Our gravity is doing the same thing it just did, with our mg times this h, because we want it to go the same distance. The only difference now is we have friction involved. Right, so we have our 1/2 mv1 squared minus mg, I'm going to replace it now, it's the d sine theta, plus our work from friction equals 0. So now we just need to figure out the work from friction. So our work from friction is our force of friction times the displacement. So we just need the force of friction. Well, the force of friction, given this mu k, right, we know it's the normal force times mu k. And our normal force, so again, since we're not jumping off of a thing, here's we start thinking about some of our forces again. If I break my gravity into my two directions, then the normal force, since we're not accelerating this way, is going to have to be equal to this component of gravity. So we can say that our normal force, so our friction force is mu k times our normal force, and our normal force is going to be mg cosine theta. So that's our force due to friction, and now we multiply by the distance traveled, which is just our d, because our friction is acting along the ramp, and that's how far we're going along the ramp. So now we just plug everything in and solve for our v initial, right? Because we have one equation, one unknown if we plug this in. And also, lo and behold, we don't know the mass, but it's in every term again. So we can just divide that out. It's going to end up with 1/2 v1 squared minus mg, not m, sorry, minus g d sine theta equals, one thing I forgot to think about, right? Our displacement is going up the ramp, but our friction's going down. Our work from friction is going to be negative, right? d sine theta minus mu k mg cos theta d equals 0. Obviously, we can simplify this a bit more. We can simplify this and work on actually isolating that variable, because hypothetically we know everything else. We just do the same thing we did where we bump it to the other side, multiply by 2, and take the square root. I'm just not going to bother doing that right now because I think you all know the algebra, just to work through that, finish that one out on your own. Right? So now how fast is it moving when it hits the bottom of the ramp? So this is a thing to think about, right? Before we said it was just the same because the work done by gravity going up was just undone by it when it was going down. But this time as we go up, we also have friction. But as we're going down, we still have friction, but the friction changes direction. So now if I grab this and I switch my directions, now we're starting up here. I'm looking at how fast it goes when it comes from the top and goes to the bottom. I'm going to call this now our V2. This is now the V1. And we're still starting from rest. Now we have to think about the fact that our friction is going to be opposing that direction of motion. Our normal force is still this way. Our gravity is still this way. So now our gravity is going more towards it's pulling more down. Our y displacement is going down and our gravity is going down. So now gravity is going to be doing positive work instead of negative. But our friction is still doing negative work because it's still going opposite the direction of motion. So if I set this up, I do 1/2 mv1 squared plus work from gravity plus the work from friction equals 1/2 mv2 squared. Again, because I said the work from the normal force is still going to be 0 because we're still not jumping up off that ramp. I said my initial velocity is 0, so that can go away. We said our work, it's the same magnitude as it was before, but it's positive, right? Because they're going in the same direction. So we're going to have mgd sine theta. And then this, again, same distance, same everything, and it's still going in the negative direction, so that's going to be minus mu k mg cos theta d, which is going to equal 1/2 mv2 squared. And we're trying to solve for this v2. We can divide out by m through the whole thing because every term has m in it. And now we can say that our solving for this velocity, I'm just going to half solve it. We got 2g d. I'm going to factor these out as well. So you have sine theta minus mu k cos theta. And that equals, I multiplied by 2. And then if I take the square root of both sides, here's our solution for our V2, which is different from our initial velocity that we said from before. Right? If I were to solve this out, it would look different because our friction was slowing it down. Before, the gravity did something and then it undid itself, so it's going to be the same. But this time, the friction isn't undoing itself, it's slowing it down more. Right? The kinetic friction is different from other forces in the problem. We call that, it's not conservative. Right? It's not a conservative force. It means that we can't just look at the initial state and the final state, right? Because if I looked at the initial state here, and I was looking at, if I looked at the initial instant that I pushed it, and then it goes up, it comes back down, and I look at the instant that it's back at the bottom, if I just took those two pictures, I wouldn't be able to tell the difference between them. Right? I would want to say that those were the same state, but I can't say that because friction has happened in between. It depends on the path that I took to get from my state 1 back to my state 1. Because if I just went here to here, our distance for the friction would be smaller, and it would have a different impact. We went all the way up, all the way back down, that has a different impact. It depends on how I get from point A to point B. If I just went like that, like in a straight line, that works. But if I go loop-de-doo all crazy, if I was looking at the work done by gravity, that wouldn't matter. Because I could say that my work done by gravity to get from here to here, if I'm saying that this is my y direction, right? If this is like up in the air, the initial force from gravity, the initial placement is the same as this. We don't have any displacement in our gravity direction. Therefore, we don't have any work done by gravity. And now we're just looking at this last problem. Problem 3, right? We have a police officer with a speed trap. Our speed limit is 30 meters per second. And the driver is measured to be traveling 25 meters per second. Then she slams on the brakes when she sees the police officer, right? And she gets pulled over anyways and gets a ticket, all this jazz. So, but now she's trying to contest it by saying, I left tire marks on the ground when I slammed on the brakes. So we have to see if it was possible. We have to see how fast she was going before she slams on her brakes. Because if it's less than 30 meters per second, then she wasn't speeding. But if it's greater than 30 meters per second, then she was. Right? So we have our final velocity. So we know at the end, I'm going to just start marking this, our V final, 25 meters per second. We have our V initial is what we're solving for. I'm going to use V naught actually. V naught, that's what we're solving for. And now let's start thinking about when we have our 10.6 meters, that's going to be our displacement, our change in distance. So if I'm drawing this as a picture, right, we have our car in our first spot, and our car here, right? This is where we have our V naught. This is where we have our V final. We know that between the two, we left tire marks. This is not a good drawing, I'm sorry, but we have tire marks between that says it took 10.6 meters of kinetic friction to drag and slow the car down to this 25 meters per second. So let's figure out how fast she was going before she slams on the brakes. So let's set up our work energy. 1/2 mv naught squared plus all of our work. Just a big W, not that weird. And that has to equal our 1/2 mv final squared. Right, we have our V final. Now let's figure out what forces are acting on our car so we can figure out the forces that could be doing work on the car. So while it's skidding along the ground, we have gravity pulling it down, normal force pushing it back up, and we have our force of kinetic friction that's slowing it down. That's what's actually doing the slowing down. So let's think about which of them is doing work. So we have potential for work from gravity, work from our normal force, and work from our kinetic friction. Let's think about what's going on. We're not jumping up into the air, right? So we're not displacing at all in the y direction. So there's no displacement in the normal direction, and there's also no displacement in the g direction because they're both in the y direction. So both of the displacements for these is going to be 0. So both of the works for these is also going to be 0. Now let's look at our kinetic friction. So we know through our, again, since we're not accelerating in the y direction, we can say that that's supposed to be a sigma. Sum of the forces in the y direction equals, right, we have our normal force acting up minus our gravity going down, and that equals, since our acceleration is 0, that equals 0. So we know that our normal force equals our gravity, right? We just do a quick force balance to get our normal force, and then from there we have our mu and our normal force to give us our friction force. So we can say that our force from friction is our mu k Fn, which, since it's equal to our force from gravity, which is just mg, that's going to be mu k mg. So we have a force from friction, right? Because our work from friction is going to be force times our distance, which we said was our 10.6. So we have our force from friction now, right over here. So if we plug this in, it's going to be our mu k mg times 10.6. That's going to be our work from friction. But now we think about positive or negative, right? The car is going in this direction, our friction's acting in this direction. So here's our displacement vector going to the right, friction's going to the left. They're going in opposite directions, so it's going to be our negative work. So plugging this back into our equation up here, right, let's think 1/2 mv0 squared minus mu k mg times our 10.6 equals our 1/2 mv final squared. Now every term here has an m, so you can cancel those out. Just ding, ding, ding. And then I'm going to solve for our v0 on one side so that we can solve for v0, right? Because that's what the question's asking for. We're trying to figure out if she was speeding before she slammed on the brakes. So solving, I'm going to subtract this over, or add this over to the other side and multiply by 2. So you get that our v0 squared is 2 times our mu k g times 10.6 plus v final squared, right? Because I multiplied by 2, so the 1/2 goes away, and we divided everything by m, so it all works out. And then to just isolate our v0, we just take our square root. So our v0 equals the square root of 2 mu kg 10.6 plus v final squared. And that is a equation, and now we have to think, what do we know, what do we not know, right? We knew our displacement, we know our final velocity, that's the 25 meters per second that she was measured as having traveled at. G, obviously we know. The only thing we don't really know is our mu k. It's not given in the problem, but we need to figure out the frictional force. We have to estimate our coefficient of friction. So, estimating our coefficient of friction doesn't really matter as long as we're close. However, I know that the rough estimate is a mu k between tires and pavement. It's around 0.7. I just know these things, it's okay. So now we can find that our initial velocity, right, is our 2 times that mu k times our g times our 10.6 plus our 25 meters per second squared. Sorry, not meters per second squared. 25 meters per second squared. Right, it's a velocity squared, not an acceleration. And then punching all this into your calculator, you're going to get that she was going at 27.75932,996 meters per second before she slams on her brakes. So she wasn't lying. Well, the tire marks being that long means there's no way she could have been speeding before she slams on the brakes, because the friction wouldn't have done enough work to slow her down that much. So we know that she's telling the truth, and now she has avoided a ticket. All right, so I hope this video was at least a little bit helpful. Let me know if you have any more questions about this recitation or anything else that you want me to try to explain. And I'll do my best to try to explain it, because I guess Sydney explains stuff.